time. The doorbell rings as soon as I say that, but that's okay.
Twice.
Always. So let me start by asking about homework. How's homework 2 going? Yeah, I believe there is a bimodal distribution from what I could tell. There is a pile of people who have turned it in and a pile of people who have not started. So I'm not going to ask each of you in public which pile you're in. You all know, but if there's any questions that you'd like to ask, I'm happy to answer them in this format because chances are someone else has the same question. Anything that I can go over as a group that would be helpful for homework 2, which is due tomorrow night, Wednesday.
Can we talk a little bit about the residual variance and
Yes.
what that encompasses, what that means?
Okay, sure thing. So Sam, the TA, asked about doing residual variance as a concept of review. Let me open up the homework so I can do it in this context. Okay, let me move this over here so we can all see. And Zoomers, I'll get the screen share going so you can see. How about that? I know, bonus points for me remembering. So there are instructions that are general in terms of just what you should be doing throughout the assignment. There are also section-specific instructions that say what the model should contain. So make sure you're looking at all the blue text in terms of what to do. With respect to the residual variance, this is one of the 2 things that I ask for troubleshooting purposes. So in section 1, for instance, predict the number of fits thrown. So this is a preschool example. I know many of you don't have children, but most of you were a child at some point, I can assume, or have been around children. And preschoolers are volatile little people. You've heard of the expression, the terrible 2s? No, it's the terrible 4s. My son became a nightmare when he was 4. He actually got kicked out of preschool on 2 separate occasions. They called us to come get him because he wouldn't calm down after being told no about something.
Wow.
Yeah. And the first time he's just like, well, I didn't want to be there anymore. I wanted to come home and play. I said, oh, hell no, buddy. Nope. So he came to work with me that afternoon, and I had like this little like letter number activity book, and I'm like, nope, you are working. This is a work day. You got yourself kicked out of school. You are going to work. So I have fits thrown as the dependent variable in this story. That one of the predictors is how many times they said please, because these children can also be very sweet at the same time that they're very volatile. So predicting number of fits thrown from an empty model means we have no predictors, right? So the role of an empty model is to reconstitute the mean of the predictor as the fixed intercept and the mean of the outcome as the fixed intercept, and the variance of the outcome as the residual variance. So if nothing is predicting y, then your E variance, residual variance, is all the variance in y to start with. And I asked this question first, you can see all the other numbers I've tried for previous homeworks, because if you don't get this right, you do not have the right model. You don't have the right outcome or the right predictors. So this is a check to make sure that your specification is correct. The second check, fixed intercept, is checking your centering. So for instance, in section 2, please is heard is to be centered such that 0 equals 7. So that means make a new variable by subtracting 7 off the old one and put the new variable in as your predictor. If you forget that step, then everything will be right with respect to the slopes, because the slopes don't care about where the predictor is centered. The intercept cares. So if you get this stuff wrong regarding the intercept, but you have your residual variance correct, then that means you have not centered your predictor correctly. It's because the intercept is the expected outcome specifically when x is 0. So your 0 is not in the right spot, but that is incorrect. Okay, did you want me to do more on definitions of residual variance?
Yeah.
On that?
With the definition and like with the results section at the very last question for sections 2 and 3.
Okay.
Talking about the residual variance and what that means.
Okay, so suggestion from the TA. So Question 1, conceptually, section 1 rather, question 1 of section 1, this is all the variance there is in the outcome variable of fits thrown. In an empty model, it returns all of the variance. You would get the exact same number if you ran descriptives and asked for the variance of that variable to be printed. So this is as bad of a job at predicting this outcome as you can do, is because you're predicting it with nothing but a single fixed intercept. So everybody has the same amount of fits predicted. In section 2, we are adding pleases heard as a linear slope, so expecting a linear relationship between fits thrown and pleases heard. And so the difference between section 1 and section 2 is this one new predictor variable. So the last question of section 2 and a parallel question for section 3 asks, and note that all of these are 0 because I haven't filled in my numbers yet. These get populated with your answers after you submit them, but they're not necessarily the correct answers, it's your answers. That's an important point. So whatever you typed in the boxes gets populated down here in these spots. Like each of these is a database reference pull to your row of your data set. So there's a question here about what happened to the model residual variance, and the choices are significantly or non-significantly, and then larger or smaller. Well, larger or smaller, you can just literally look at the two numbers and decide which way it goes. And significantly or not is determined by what makes the model different. So if I start with the model in section 1 that has only a fixed intercept, and I add to it a slope for my new predictor, then it has to be the slope that's doing the work to make it different. That's what differentiates the two models, so any differences in the residual variance has to be due to that new component. And so then the significantly or not would be due to what happens given that new addition to the model. There, I've danced around the answers but not quite said them explicitly. I'm not sure I can say more without just saying the answer, but does that help? Okay. Erica, do you have any suggestions for review things folks that talk to you about? I caught it? Okay. All right, any questions from the rest of the group here? No, head scratching, not question. Okay. All right, then.
The second question.
Second question?
Yeah, I'm sorry. What was that?
Yeah, can we just walk through, like, conceptually and I guess definitionally?
Definition.
Cohen's D.
Cohen's D.
Yes.
Yes. Cohen's D is an effect size.
Cohen's D.
Yes, that one is, that is one of the few things that is not directly in your output that you have to go and track down. So let me open example 2 again so I can show you where that is. So it's discussed, I want to say page 11. I was just referring to this. Let me find it again.
Yeah,
Oh, yeah, so let's do the other one too. So there are 2 questions on here that I've gotten a lot of questions about related to effect size. So in section 2, there is asking for standardized estimates. Those are standardized slopes, and those are given to you with an extra piece of output. There is an example of what that would require on page 7 out of 11. This is example 2. So to get a standardized slope as an effect size, that's in a correlation metric, you add the option beta after the comma under regress, and then it's shown way out here on the right-hand side. Note there's a dot here because your fixed intercept is always standardized to 0. Always. In R, it's one more little piece of code, lm.beta. And you should have loaded the package where that came from as part of your starter syntax file. For Cohen's D, that is also an effect size. It refers to standardized mean difference, so it's how many standard deviations apart 2 groups are. And so D is more useful in a 2-group comparison for an effect size rather than a continuous slope predictor. This is one that you have to construct out of the saved output. So the formula for Cohen's D, there's a lot of ways to get it, and so you may have seen this before just in terms of just 2 differences in a mean divided by a standard deviation. This is a more general way to get it in the context of a model that may have other predictors too. So it's 2 times the t-test statistic that goes with the slope you're trying to get the effect size for, divided by the square root of denominator degrees of freedom, which is your sample size minus the number of fixed effects. So I have the math in here for this particular example. The way that I would prefer that you go about doing this is to extract the saved output so that you have the number as precisely as possible. So in Stata, I have commands that went with the model. First off, let me find it. This command right here generates a new object inside Stata called Mary results that is the saved output from your analysis. You can then print that object. So matrix list prints it. And so this is showing you, this is the slope that I care about. There's the estimate, standard error, here's the t. If I think of this as a grid or a matrix, this is in row 3, column 1. So then down here, I asked it to do the math. 2 times, and that's where t goes, because that's the cell reference to where t is saved, right here. So it's going to go into that object, pull out that number, and do the math for you, and then divide by, this thing is an internally saved object for denominator degrees of freedom. You could also find it from right here. So that's how I would compute Cohen's d in Stata, standardized mean difference. To do it in R, it's the same concept, but just different code. So inside the object for where my results are stored, which is called model Mary 01 for me, coefficients is a list inside there. And so I'm asking it to print the third column of that list. So this is the t-test statistic. And then I'm accessing that and doing the formula right here. So this code should work straight away for you. You shouldn't have to change anything except the name of the object that it's pointing to. Because it's a 2-variable problem, or 1 slope at a time, 1 intercept at a time problem. 2-parameter problem, I should say. Okay, does that help? Okay. So again, pages 9 and 10 is where you can find the code to do D. And I would recommend, by the way, going to the source files for these. Don't work from the handout. Like, I have all of this typed in an R script that you can just copy from directly. Same thing with the Stata code. There's a direct do file is what the syntax is filed. Okay, other things you want to talk about for this. All right, then as a reminder, I'm leaving next week. So there's no class next week. I may make some videos, I may not. We'll see how far we get and how we are in the schedule. At a minimum, I will leave you with a formative assessment to work on. If the stars aligned and I can get it done in time and to the TAs in time, you might have your next homework you could get started on as well. We'll see. I'll let you know, okay? But otherwise, no classes next week. Take a breather. Take a nap. Hell.
Yeah.
2 o'clock in the afternoon is prime napping time. That's what I say. I won't tell anyone, I promise. But I do value your mental well-being, and sometimes you just need a nap.
Yeah.
I know for me, like the point of when I get to where I can't do any more work, right? We all have these signs where we can see our brain is just fried. It's when I spell there, and there incorrectly when I'm typing an email. If I do that, I'm like, step away. Go take a nap, go do a run, go do laundry, go do something. Just, you're done. So, week 6 and 7 in the semester, we may start to feel that way. Might need a nap. But in the meantime, we're here this week. And I promised you F as a new addition to your letter toolbook. Remember? Like, did you say F? Yeah, F. And F may stand for many things in your heads. But this is not the F that you're probably thinking of. So to reorient us to what we're talking about in this unit, the idea is still examining the relationship between one X predictor variable and one Y outcome variable. But now that relationship is going to require more than one slope to fully describe. That's the idea. So the first example of this we saw is in predicting income using the same data set here, general social survey data, from self-reported working class status. So folks were asked, do you consider yourself lower class, middle class, or upper class? And they selected their answer. So what kind of variable would you describe this as? Let's do categorical or quantitative. Categorical. I have these numbered 1, 2, and 3. Are these numbers? Not really. I would say this is an ordinal variable, maybe. Like we could say that upper is more than middle is more than lower. Now, if I tried to take this variable as it is now, stored in my data set 1, 2, 3, as the choices, if I fit a linear slope through it, first of all, would my software let me?
Yes.
Yes, it will. Would that linear slope mean anything?
No.
Not really. Another way of saying it is that a linear slope is the same change in y for each increment change in x. So a linear slope would say the difference in income between middle and lower is the same difference in income as there is from upper to middle. That, at the very least, is a testable assumption. If this were a nominal variable, like, dog, cat, bird, or something like that, then the numbers would be even less of numbers, and it really wouldn't make sense to put a slope through it. So to fix that, what we have to do is reconceptualize this predictor into a series of binary ones, and more generally, we need C-1 new predictors for a variable with C categories. So I've got 3 groups here, C is 3. I need to make 2 new predictors, and I need to give them each a slope. Each of these new predictors is binary, 0s and 1s. This coding scheme is known as indicator coding. This is slide 6 that we're on here. Let me zoom in a little bit. Step 1 is to decide who you want as your reference group. They get 0s for all their new predictor variables because the intercept is going to be the expected outcome when your predictors are all 0. That sets it up to be for the lower group. That is an arbitrary choice. You get to make that choice. Lower because it's first, lower because it's most common. Sure. Then, my first variable, what I intend it to capture is the difference between middle and lower. So I flip middle to 1. Think of it as like a light switch. Like this variable is getting turned on for the rows that have middle as their answer choice. And I leave upper set to 0. Now, if all I had in my model was this column right here, do you think this would work as intended? It would not, because I would get lower and upper combined versus middle, right? Because this is 0 and this is 0. So I fix it by adding a second column that splits out lower and upper. So the two work together to separate all 3 groups. So at the end of this, we end up with 3 terms as fixed effects. My fixed intercept, which is what it's going to be for lower. Beta 1 tells me how different middle is from lower. Beta 2 tells me how different upper is from lower. And so that's why I've named these predictors the way that I have. In general, my naming is like the 0 group versus the 1 group for these sorts of variables. Now, I only have 1 group mean and 2 group differences, but I can do the math to get all the other combinations. And that's what I'll show you how to do in software, hopefully later today. I don't want to spend a lot of time going back over this logic here because I want to do it in the context of the code that makes it happen. I think that will be more useful. But I just wanted you to recall the story here. So we're adding 2 new binary predictors to represent 3 groups and their differences. And because I have 3 fixed effects and 3 group means to be captured, it will work perfectly. Okay, does that sound familiar?
Mm-hmm.
Maybe? If I had 4 groups, how many new predictors do I need to make? 3. If I had 5 groups? 4. Yeah. Guess how many groups you're going to have in your next homework 3?
10.
No. Do I look that mean?
It's no harder than 3.
You're going to
Work
have
under
4.
our code.
You're going to have 4 because I showed you what the logic should be. So it's can you extrapolate the code to turn it from 3 groups into 4?
Okay.
And I promise you, I think I said this to the other class this morning, my goal is to give you an exact example or template for everything I'm going to ask you to do. You do not need to Google or ChatGPT to figure out the codes, okay? You should be able to extrapolate, and if not, please ask for help. Okay? They pay us. Actually, sorry, Sam, you're not getting paid. I know.
He does it for the love of the course.
He's getting course credit, so he's technically paying us to work for us, I think.
ACT is paying us.
Okay, yeah, it's not your money. That's the important thing. But yeah, that is my job, right? And that's Erica's job. She's being paid. So don't feel like you're, like you shouldn't ask us for help. That is literally what we're being paid for. So, okay? Zoomers, I'm still looking down at you. Yeah, you get to see a whole lot of my neck. I apologize, but this is the angle that we get here. So we did this whole thing where we looked through like, how do the parameters rearrange themselves to give all the differences and all that stuff. But where we left off, I believe, was slide 11, which is what I'd like to start with in terms of new content. So here is an example model for one variable that has 3 groups as a predictor. And if you were learning this in another class, what would you call this model? It has a special name and it's on the slide somewhere.
Multiple regression.
Oh, no, I would call it that, but no, it has another name. It starts with an A.
ANOVA?
Mm. This is a one-way ANOVA. That's what this is. Now, this is not at all how I learned ANOVA. I learned it with like boxes and like cells and margins and stuff like that. This is the linear model's representation of an analysis of variance. A one-way analysis, meaning there's one predictor that has more than 2 levels. If it were only 2 levels, people would call that an independent sample or 2-sample t-test. I think that's a dumb name though, because t isn't everything. Like t is going to show up the entire semester whether we're doing a t-test or not. So I don't like that one. But anywho, so we can go into the details of this, figure out which groups are different from each other and all that stuff. But each of these details on its own is insufficient for answering a more general research question: does group membership matter? Like, does this variable predict income or not? We don't really have one answer to that question yet. So that's the new part that I wanted to bring you starting now. The answer to this question requires considering the slopes jointly and how well they work together to predict an outcome. So what I want to do is ask, do they both predict this thing, like simultaneously, jointly? Wording this a couple different ways, I can say, is the residual variance from this model that has these 2 grouping predictors, so these 2 variables right now in this example, significantly lower than the total variance that we started with? That's one way of talking about it. Now, this is the exact same question that's at the end of your homework that we discussed earlier today. The last question in section 2 and section 3 is this question. In your homework, it's a very easy question to answer because each model has 1 slope. So if that slope is significant, the residual variance is less, the end. This, I got 2 slopes. So I need to consider both of them as a set to answer that question. Did the residual variance decrease significantly after including this predictor or not? Another way to say the same thing is y hat. The prediction from the model here, is that predicted y significantly correlated with the real one? That's another way to say the same thing. So is there a relationship between what my model says income should be and what income actually is in my data set? That's what we want to know. So the more general term for this, new vocabulary, multivariate, meaning more than one variable at a time, wall test. Got a question. What makes something significant? Like if I can tell if something is lower or higher, what makes it significant? Great question. For each of, let me see here, went back too far. For each of these terms, beta 1, beta 2, we're going to get a line on our output that first gives the estimate. That's the answer for what that slope is according to our sample data. That makes the e's collectively the smallest. It minimizes the sums of squares of residual for its objective function, if you want to say it that way. And each of those slopes then has a standard error describing its expected inconsistency, the average difference from that sample slope relative to the population slope. Next column over is t. That is estimate divided by standard error. T is telling you where you are on the goalposts. So t of 2-ish is usually the standard for where significance starts. But the next column over is the answer. That's your p-value column. That should be less than your chosen alpha to declare it significant. So if I say alpha is 0.05, if p is less than 0.05, we label that slope as significant. If if p is less than or equal to 0.05, then it would be non-significant. The same thing is going to happen for this as a joint test. It's just that it's a new p-value that we're now going to interpret rather than ignore. It's already been in the output, but we've been ignoring it because we didn't need it. And positive or negative is the sign. So each slope has a sign that's either positive or negative that goes with its label. In what we're talking about here, it's always going to be a positive number because it's going to be in squared units instead. But we'll get there. All right, does that help answer the question, Zoomers? Okay. All right, so we're asking a different question. Beta 2 and beta 1, how well do they work together to predict y? That's what we're asking. This is an example of a multivariate wall test, meaning we're lumping together multiple slopes and testing them as a set. In order to do this, we have to quantify a couple of things. We're asking how well our slopes predict this outcome relative to how many slopes it took to do so. So if you add a whole bunch of slopes, you should predict your outcome pretty well. But the question is like, how good is each sort of on average? So relative is quantified using two types of degrees of freedom. One of them is called numerator, one is called denominator. So the total is the number of fixed effects that is possible, which is your sample size. So numerator is what it's going to be called. This is a new vocabulary word. Is computed as k minus 1 because the intercept doesn't count. It is the number of fixed slopes in your model. So in our example with 3 groups, I have 2 fixed slopes. Denominator is how many degrees of freedom left over you have, how many more slopes you could possibly add. That's what it means. How much room you have to be wrong still. We also need to come up with a way to index how useful each slope is. And this is going to show up in your output as something called sum of squares. What that refers to is the numerator in the formula to compute variance, this term right here. So if total sums of squares would be this. It becomes variance if you divide by n minus 1. So this is y minus the mean in this case. So this is like if this is the square, this is the sum. That's where the term comes from. All right. Model prediction then is taking into account all of these things at the same time. So we first want to know how much information did the model pick up with our slopes relative to how many slopes did it take. That's going to be called mean square for the model. And then how much is left over. How much information is still out there in the e's. So y minus what y hat, what it's supposed to be, that's e. And then how many slopes could we still add to explain that leftover variation? And this is residual. This is usually displayed in a table like this. Now I know this is a lot, so I want to give you a real-world example that goes with this. Can I do that as best I can? Anyway? I don't know if it'll work, but I'm going to try. The theme of this example is shopping at Kohl's. Kohl's department store, one of my favorite places to shop. And if you spend, let me put it this way, if you pay full price for something at Kohl's, you are doing it wrong, okay? That's just not possible. Kohl's constantly puts everything on sale. They email you or paper mail you coupons to spend in the store. If you go and return something from Amazon at Kohl's, they give you a coupon to spend in the store for returning something at Amazon. And then when you buy stuff, you get Kohl's cash, which is even more money to spend in the store. So there's no possible way you're spending full price on anything. But all of these gimmicks makes it sort of difficult to figure out how much you're actually going to spend on something. So my mother loves Kohl's as much as I do, and she's prone to call me up and tell me about our shopping trip. She's retired, so, you know, this would be worthy of a phone call. You won't believe how good of a deal I got at Kohl's this week. I got this and this and this and this, and guess how much I paid for it? Right? So she is describing to me in her own way the contents of this table. The question is, how much money did she spend? How much then is it like per item? That's what constitutes a good deal. So if she only spent $15 and she bought 3 things, and that's $5 a piece, that's a good deal. If she spent $15 and she only got 1 thing, maybe that's not as good of a deal. But to get a sense as to how good of a deal it is, we also have to know what's left in the store. Like, what could she have bought that she didn't get? Because not paying for things that are badly priced is also part of a good deal. So if you think of it from that sort of lens, like the model is what you bought, okay? So this should be a little hatty thing over here. I don't know why it's not showing up on the PowerPoint very well. But this term right here is essentially saying, like, how much information did the model account for? And I'm saying information because this isn't variance yet, it's just the numerator. This is like, how much money did you spend? And this is, how many things did you buy? How many slopes did it take to capture this much information? So the rate of good deal is money spent per slope, or per thing bought, for some kind of average deal. How much did your purchases cost on average? That's mean square model. So this is like, how good did I do as a function of how many slopes it took to get to that level of prediction? So if I had one slope that was really, really useful and one slope that sucked, then they'd sort of average each other out to be medium useful, because this is an average per slope included, per thing purchased. Residual is like what's left in the store. So what is all the information that's left over in our E's that we don't know why it's there? What's all the stuff we chose not to buy? How many more things could we have bought? How many more slopes could we have added? And so this is a ratio of those things. Mean square residual is your residual variance. And so what you got versus what you could have done is then a ratio that forms a new statistic called F. Effect size is built out of this column right here. So welcome to another new letter besides F, R square. You know what R is, right? Can you guess how I get from R to R square? You square it. And for reasons that I've never understood, it becomes capitalized when you square it. Like, it's more important now. So there's 2 different ways to think about this. R square is a measure of how successful we were at predicting our outcome variable. It is the proportion of variance explained by the model relative to what is left over. So sums of squares total, that's all the information that our predictors captured. Residual is all the information we don't know about yet. And then total is the 2 put together. So it's computed in this way. And there was at least one person who emailed me and had the wrong answer for residual variance, and it's because they were extracting the variance of the residuals as an R output and not doing it this way. So those will not lead to exactly the same thing. This is how it's computed using linear models. It makes sure that it's positive. A more, I think, direct way of thinking about it is, okay, what if we made a y hat for everybody? Y hat is what the model says your outcome should be, right? The red part, intercept plus effects of slopes and stuff. Every software package has an option to make a y hat column in your data set. I'll show you how to do that. If I take that y hat column and I correlate it with the actual y, that's R. And if I square that, that's R squared. So R squared you can think of as the square between the model predicted outcome and the real one. You can also think of it as the proportion reduction in the residual variance relative to the empty model. Either one of those is accurate. And then F is the significance test for whether or not R squared is greater than 0. Now note that we're in squared land here. Square, 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 square. Now I'm making that point because guess what F can be? 0 to positive. F cannot be negative. Everything is in squared units here. The reason for that is that we don't want the slopes to cancel out. Like if one slope were negative and one slope were positive, we want to make sure that everything stays in the right direction. So F is a new test statistic. It is only positive, and it is going to tell us in this context how successfully the slopes work together to predict this outcome, whether our R-square for variance explained is greater than 0. And here are a couple different ways that you can think of F. One of these formulas might be more useful than the other. I like the one on the left. It is how much information did we capture per slope divided by how much information is left over that we didn't capture per slope we could have added. What we have over what's left. Worst case scenario, they're equal and they're 1. Best case scenario, F is much bigger than 1. Okay. Questions on that concept? I know it's a new one. Big picture, what we're trying to do is ask as a global level, how useful is our model? All the slopes together. So this is finding a way to put them together to capture how much information they've gathered per slope divided by information left over per slope left over we could have added. F is a measure of did we get a good deal. R-square is an effect size for how good of a deal we got. Here's F. These are F distributions. F is the older sibling of T. Do you remember how T and Z, remember that whole thing? Like Z is the normal distribution, and then Guinness, factory worker, figured out that Z didn't work for him and he made up the T distribution instead, and T is like flatter as you get smaller. F works the same way. But F looks like this because it's only positive. F is in squared units. So F has two values when it's written like this: numerator degrees of freedom, denominator degrees of freedom. Numerator degrees of freedom, the first number is how many slopes did it take to get to this level of F? Denominator is how many more could you have added? So F has different shapes based on the degrees of freedom. And here's a bunch of pictures of them. And here's where I stole the pictures from. I'm not going to reinvent the wheel. If you Google F distribution, you'll find 8,000 pictures that are perfectly fine. So trying to put all of this together, and I'm glad you asked the question earlier, Zoomers, about what means significant, because we're adding to that list right now. Here's a table that will tell you about the possibilities. So step 1, choose your alpha. Alpha is false alarm rate or miss rate. We talked about this 2 weeks ago, I think, bringing it back. Alpha level. Is it type 1 or type 2 error rate? We'll go with that.
Type 1.
It's type 1. Is type 1 a false alarm or a miss? It's a false alarm. So alpha is the percent of the time that you're willing to be wrong if you declare something sufficiently unexpected, but in reality, it's part of a normal distribution just on the tails. So 0.05 is the traditional alpha level for the social sciences, for better or worse. We're saying 5% of the time we're willing to say, yes, this is significant, I found something, even if in reality the truth is that there's nothing to find. 2.5% of the time I'd find something positive, 2.5% of the time I'd find something negative. This way for your range. And possible directions in this class, it's two-tailed always, because most slopes can be either positive or negative. So then based on that, we would be looking for a p-value that's less than 0.05. The test statistic that goes with it is going to be one of these 4 things. And this is a more general thing you'll find across all quantitative methods, not just this set of models. If we are testing one slope, and we are willing to say that we have infinite sample size, that slope can be tested with a z. Estimate divided by standard error is placed on a z distribution where your goalposts are. Most of the time, we're not willing to say infinite sample size, so we replace z with t. That's what we're going to do. So this is old content, so to speak. The new part is this column right here. If we are simultaneously testing 2 or more slopes at a time, then the analog to z is called chi-square. That looks a lot like F, except it doesn't have the second number. So it only changes as a function of the first number. If we are not willing to say we have infinite sample size, then the analog to t when we test more than one slope at a time is f. And if we're testing one slope, t squared is f, and z squared is chi-square, which is why I said we could ignore the front table that had all this information because it was redundant with the one slope that we got. So if your test statistic, one of these four things, exceeds your goalposts, the critical values where you decided unexpected starts, that means the p-value you get on your output is less than the chosen alpha. I would say I reject the null hypothesis. This result is significant. If the t-test statistic, or f in this case too, does not exceed the critical value, you're inside the boundaries, then I would say we have a non-significant result, or not significant. I would say do not reject or retain the null. So numerator degrees of freedom is the new part here. How many slopes are we testing? Denominator degrees of freedom is based on n. So if you only have one slope, the t-test for it is f. And that's why we didn't have to pay attention to f up until this point, because we only had one slope at a time. Yeah. Okay. So then, with one predictor, here's why. Like homework 2. Homework 2 looks like this. You have fit count as your y. You have pleases heard as your x in section 2, or you have age 3 or 4 in section 3. So in that context, where you only have one slope in the model, the significance for that comes from the test of the slope directly, estimate divided by the null hypothesis, or minus the null hypothesis, excuse me, divided by standard error is your t. If I square that t, that would be f. So I didn't make you look at f because it was redundant. It's the same information. The p-value will match exactly. And the r that gives the standardized effect size for how correlated the predicted y is with the actual one, if you squared that, would become r squared. So this table, you're going to start seeing on your output. This is the one I told you could ignore. We can't ignore it anymore because we're going to have more than one slope in the model at a time. So with two or more fixed slopes, we do need to pay attention to this. The question of how well they work together is a separate question than how well each of them works by themselves. So on our output for this example, this is what we're going to see. These are the numbers that are going to show up on your output. So what do we know? Sums of squares model, that's how much information we were able to capture. Numerator degrees of freedom, how many slopes did it take? Sums of squares divided by degrees of freedom is that one. Same thing on residual, but now it's how much is left over. How much don't we know about? Divided by how many slopes could we still add? That's mean square residual, that's your residual variance. And then here's the total, which normally doesn't show anything in these other boxes. Okay. 245. How are we doing? Thumb check? Okay, we got some upness. The numbers, how are we doing? Thumb sideways? Sideways to down? You can be honest. We have some, I don't even know what to call that emoji, but it's like this. It's that one. Is that a good imitation? Yeah, nonverbal communication works for this. Yeah, and you know what? The correct answer is honestly somewhere in here, because it's like, what is all of this? Like, what? Which is why we go back over things, because it doesn't sink in the first couple times. Do you want to see it work in practice? Want to see some codes and stuff? Yeah, that usually helps me at least. I have a hard time with abstract things. I do much better with concrete examples. So this is example 3. We can work through this. Let me switch gears for a minute and we'll go through this. So this is the same data set, predicting income in thousands of dollars. This example is going to have, I think, 3 different predictors, maybe 4. Yeah, 3 category working class is what we're working with right now. Step 1, tell your software where your stuff is. Always. So this is the part right here, just as a reminder, if you're using the University of Iowa virtual desktop and your stuff is stored somewhere on your local machine, you need to have this prefix so that it will find it. So like from here after that, that's my local file structure, and you would want to paste in yours instead. I'm importing the Excel data. Here are the labels for the things we're going to be looking at in this example. Work class is the predictor that's new to the story. In R, note that I have included code in this example to load all of these packages that we're going to be using. I have to do the same thing in terms of setting a working directory. That is where this stuff is coming from. I am importing the same Excel data set we used in examples 1 and 2, making sure that it is as a data frame as needed to run most of these analyses. Okay. Step 1, always data description. Always make sure you know what variables you're working with and what their possible ranges are. So I'm using summarize in Stata to do this. I am using describe from the psych package in R, and I'm asking for the quantitative and ordinal variables in this example. Income, age, I'm eventually going to use education, and happiness. So those are the variables. Income is the one we had before, so the mean of 17, standard deviation of 13.8. For the categorical variables, I'm using tabulate in Stata. Working class is the one that we're dealing with right here. So this is lower, middle, and upper. Happiness on a 5-point scale is another one we're going to look at later in this example. And I'm using prop table in R wrapped around a table command. So example 3 is the name of the data set. Work class is the name of the column within the data set. This means if there's any missing data, make a column for that too, make an entry. And then these are the proportions that are in each category. So about 60% of the sample says they're lower class, 38% says they're middle class, and only 3% or so say they're upper class. So decidedly unbalanced across groups here, but that's not a problem. So this tells me then that I have 3 groups. How many slopes am I going to need? 2. So I got to make the predictors that are going to go with those slopes. That's my next step. For happy, this is an ordinal rating of happiness. How many slopes would I need for it if I have 5 possible levels? 4. Yeah. So here is some code to do that. This table is representing the end goal here, what we're trying to do. So first set of code, this is Stata code. Gen is the command to make a new column in Stata. It stands for generate. You can type that longer word or just gen. So I am making the LVM and LVU variables that stand for lower versus middle and lower versus upper. So this is my naming convention for this. Dots. What that's doing is initializing the column to empty values. That makes sure that I don't accidentally start with a default that doesn't get overwritten. So this is a protective way of assigning these values. And then Stata you have to read backwards. Read this part first. If the original column, called work class, is equal to 1, so note the double equals here, that's evaluating whether or not it's 1, then replace this variable with a 0. If working class is 1, replace the second variable with the 0 as well. So the fact that these are both set to 0 creates these 2 values in the table in yellow. That's what we've just done. And that's setting the lower group as the reference group. That will be what my fixed intercept gives me. And so then if it's group 2, I turn on the first to a 1, keep the second one at 0. If it's group 3, then I turn off the first one and turn on the second one as a 1. Okay, so stare at that for a second, Stata folks. Let me know if you have any questions. Okay, R folks, I'm not going to leave you out. Same idea, just a little more convoluted. NA is how you initialize a column to missing values in R. So I did that. Note example 3 is the name of the data set. followed by a $sign, and then the name of the column. So I have to embed the if working class is 1 inside this function here that selects those rows. And if this is 1, then the new variable, LVM, equals 0. If working class is 1, the second new variable, LVU, is also 0. And so the first new predictor turns on if I'm talking about group 2. The second new predictor turns on if I'm talking about group 3. So R folks, stare at that and tell me if you have any questions. And Zoomers, I'm still watching the chat and your emojis. Question, how many folks are using R? I don't know, quite a few. Yeah, I'm guessing that you all went to your advisors and said, which one should I learn? And they told you which one you should learn.
No.
No?
I
You just decided?
chose.
Yeah, well, if you're from EMS, you need to learn R for sure. I think that it's good to learn as many packages as you can, but yes, if you're overwhelmed with this, start with Stata. Stata's easier.
Would you recommend that we make that little table just to help us
Yes.
before we do the code?
Yes. Yes. I always start with like some kind of representation as to what my code is going to try to do to help myself figure it out, especially when you're new to this. Yep. Stata is designed for data analysts. That is what it's for. It's not as good, I think, as at data management kinds of things, but it does have those capabilities to do some of the same stuff that people like R for. So people can write their own packages in R. People can write their own packages for Stata. I would say that it's also continually being improved. Like new versions of Stata are constantly coming out with new cool stuff. So it's being added to much more than, say, SAS is, for instance. SAS hasn't really been updated in a long time. But one of these, that's all I need you to do. But if you're overwhelmed, I would recommend Stata. If you know you're going to be taking a lot of quant methods courses, particularly from EMS faculty, then you need to be learning R, for better or worse. All right, so here's my model then. So I just made that variable and that variable. That's what's going to go into my code. Nowhere in my model is work class, the original predictor, the 1, 2, 3 version. I don't need it. So here are the questions we're eventually going to be able to answer. I've got syntax and output for both programs here. So regress. Stata folks, what comes first after regress? As a general principle, what goes first? The outcome variable to be predicted. Yes. There's no way you would know that just from looking at the code. It's implied. What comes next are the predictors. Now, I have started doing a convention here, CDOT. This is not strictly necessary, but it is necessary for certain things, and so I've gotten in the habit of including it. It means treat it as a continuous variable. Even though this is binary, it's being treated as continuous with respect to this program. Question or head? No. Okay, more scratching. All right. I'm so eager for people to ask me questions, I'm just creating them out of thin air. So I have my 2 new predictors in here. Okay. How it knows the list of predictors is over is the comma. That means, okay, I built my model. Now I'm asking for extra pieces of output. And this is asking for a 95% confidence interval, which would correspond to a 5% alpha rate.
That stuff.
Yeah, and now here's the part we got to skip. You don't get to skip it anymore. So we have model, sums of squares. That number doesn't need to mean anything to you. It is, I think of it as the total amount of information in income that we captured by including these 2 predictors. Degrees of freedom numerator is 2. Why?
Two slopes.
2 slopes, that's why. We don't count the intercept because even the empty model had the intercept, so it's always there. So this is how much This is how much money we spent at Kohl's. This is how many things we bought. So this is the average price per thing. Residual sums of squares. That is how much information is still in our outcome that we don't know why it's there. That's how much stuff is left in the store. This is how many more slopes we could add. 731, because we have 734 people in total. That would be how many things are left in the store. So then this is the average. How much would it cost per thing you didn't buy? Mean square model divided by mean square residual. That's my F, which is over here, 42.
That's big.
It is big. So an F of 42 means like I did 42 times as good as like chance, essentially, at finding a good deal. Like what I got relative to what I would be expected to get from the leftover information is very, very good. So it tries to help you by writing it this way, because the entire world has agreed upon one way to write this, and it will look like this. So note the bold font. You are going to fill out drop-down questions that look exactly like this about 37 times, give or take. This is the formula. So it goes F, numerator degrees of freedom, denominator degrees of freedom, what F is. Now this one I'm labeling as mean square error because that's how I was taught. You could also label it as residual variance or mean square residual, but that's the 171, that's right here, that's the number that you put into the homework system to make sure your model's right. This p-value corresponds to this F. So the p-value right here in Stata is 0 to 4 decimal places. So that's telling you what proportion of the time would you expect two slopes to work together to do this good if they were both truly 0 in the population? Very, very unlikely. R square. That number tells us two things. The most direct way to interpret it is as a percentage. 10%. Including working class captured 10% of the variability in income. So 190 is where we started. That's what the empty model would give us as all the variance in our outcome variable. 171 is what's left. So we've reduced the 190 by 10% to get it down to 171. So 10% of all of the reasons why people make different amounts of money is attributable or related to their self-reported working class. Here's a softball. How much percent is left? If we know 10%, 90%'s left. So this helps sort of give us a sense as to how relatively useful this model is. It's 10% useful. In the social sciences, that's pretty good. I hate to tell you. Like an R-square of like 0.2 is about all you can hope for, like with real people and real data, unless you totally stack the deck. In your homework, I stack the deck because I control the world. So you'll have R-squares of like 0.8 or something in your homework, but that's never going to happen. So the reason why we could ignore this table before is that that F is just t squared for the one slope we had. Now that we have two slopes, this is giving us additional information. So the significance test for the model is given by this F. The effect size that goes with it is given by the R-square. They are directly related to each other. R, folks, let me do your table. So your formula has been including these two new variables right here. What's the one for again?
Your fixed effect.
The fixed intercept. You don't have to type it, but I always do to remind myself that that's first. And the default LM output does not include this table. It summarizes the table with these words down here. Some people may like that, and I don't. At least not for pedagogical purposes. Like, just seeing this all jumbled together doesn't help me. So I went looking for a table version and found this. Actually, Jonathan found it for me because I asked him if he would write a function that made this table. And he's like, someone has to have done this already. And he found one. So supernova is what it's called. I think maybe supernova was taken or something, so they just had to make it work. Supernova is just repackages that output and prints it into this format. So it has similarities to what you see in Stata. We've got a model line, and Stata had a residual line, and this is an error line. Residual and error are synonyms. You can ignore the middle two.
And
We
guess
don't
what they
need
are?
those.
What purpose do they have then?
Because they're breaking down the sums of squares attributable to each predictor.
Gotcha.
But if you look at the math, like the sum of these is not that number.
No, that's okay.
So like these numbers are not taking into account the overlap between these predictors, and so they're not as directly useful.
Gotcha,
So that's why I'm saying we can just ignore them.
perfect, thank you.
But we still have, this is how much information the model captured. Numerator degrees of freedom, that's how many slopes it took to capture it. This divided by this is this. So information per slope. Then how much is left over is right here. How many slopes could we add is right here. So this is how much divided by number of slopes we could have is right here. So then that divided by that is that. There's my f of 42. I don't need you to memorize this, okay? I just want you to understand the language and how they put together. It's like, how did you do relative to how you could have done based on what information is left? It's still the idea of found versus like expected. PRE is a term that is specific to the people who made a textbook that this is based off of. Proportion, reduction, and error. This is R square. So that's where you can find your R square in this table. You can ignore these two. And P is the p-value that goes with this F. So very similar in terms of the structure of this Stata table, just with some additional information in it. And I have deliberately highlighted in bold the numbers you need to watch for. I'm trying to make your lives easier. Like, these are the ones to pay attention to, because these are the ones that show up on your output. By the way, the reason why everyone has agreed on giving just these numbers is that if you have this information, you can work backwards to fill out the entire table. And that was like a homework problem that I did as an undergraduate in learning these models. I'm not going to make you do that either. But you can, theoretically. If you have F and you have the residual variance, then you can figure out this number. If you can figure out that number and you have the degrees of freedom, you can get back to that number and that number. So, anywho. So the same information is printed in the LM default output, but albeit in a different way. So residual standard error, that's residual standard deviation instead of residual variance. You'd have to square it, and note that it's not printed with much precision, so you probably wouldn't get the right answer. Multiple R squared, that's what we're calling R squared. F statistic is 42 on those degrees of freedom, and there's the p-value, which is 0 to 16 decimal places. In terms of the coefficients, here's your output in R. That same output is right here in Stata in a different order. Stata puts the intercept last. I know. Meh. I don't like it. No one asked me. All right, let's play. Intercept is 13. Somebody is predicted to make $13,650 on average. Who? Which group?
Lower
Lower. How do I know that?
reference group.
How do I know they're the reference? I set them that way. How did I set them that way? We're almost there. I made them 0, yes. Going back to the coding scheme. I know that the intercept is for my lower group because that's who I created my reference group out of by setting their predictors both to 0. The fixed intercept is always the predicted outcome when your predictors are 0. That means the fixed intercept is for the 0 group.
So obviously, when we're not in this class, we will choose our reference group.
Yep.
On the assignment, will you tell us what we should use for the reference group?
Yes.
Thank you.
Yes, I will control all of that.
Okay.
But the terms would just rearrange themselves for a different group, right?
Right.
So like if this group is higher by 2 and you make them the reference, now this one's lower by 2. Like it's
No,
6 to
I-
1, half
I get-
dozen.
I just-
Yeah, but yes, I will, for this reason. Yep. So yeah, the logic is like when I'm trying to get like step by step, how do I know, how do I know, how I know? All right, here we go. All right,
Okay.
so folks who called themselves lower class, beta 0, make $13,650. This is in 13,000. Okay, so L versus M, that's a slope. So a slope generically is always the change in Y for a 1 unit change in X. Now X here is going from the 0 group to the 1 group. So there's only 1 unit that's even possible to change. So 8 is how much more money the middle group makes than the low group. Because the slope turns on for them because they get the 1 in the coding scheme. So if I put these together, 13 plus 9-ish, 22,000-ish is what the predicted mean would be for the middle group. Ish. I said ish. How about this one? Who's feeling brave? Who haven't I heard from today? We get the quiet ones in here. Zoomers, you can play too. You can DM me directly, and you don't have to be wrong in front of your peers if that's a concern.
So that one is 10 more than the lower, that
Yeah.
13.
Exactly. 10 more than the 13. Yep. And here is my goalpost location. So on the picture, where the goalposts are at 2, this slope is at 8. This one is at 3. So they're decidedly outside of the goalposts. So these numbers are positive or negative? Positive. See, it's 309. I know what to expect. Softball questions. Nothing but softballs. This is 0 to 16 decimal places, and this is 0 to 3 decimal places. So would I call these positive slopes significantly positive or non-significantly positive?
Significantly.
Significantly, yeah. If my alpha is 0.05 or whatever it typically would be, these are decidedly significant. So that means that relative to how expected their fluctuation is, right, these are their standard errors. This is on average how off the sample slope would be from the population slope. Like they're 8 standard errors away from the null or 3 standard errors away from the null, way more than 2. This is how often I would get a slope of 8 if the true slope were 0. It would very, very rarely happen. This is how often I would get a slope of 11 if the true slope were 0. This standard error is much higher. Any remembrances as to why that might be? We talked about this last week, I think. Less people, yeah. There's like 3% of the sample is in this group, the upper group. So we're much less certain as to how much they differ on average because there's a lot fewer people. Yeah. So now we can answer these questions. So beta 1, middle group is higher by 8.8. Beta 2, upper group is higher by 10 point, what? 10.9, something like that, 11. So what don't we know that we might want to know? Yeah, upper and middle. Well, I can do the math. I think they're different by like 2-ish. I can get my calculator out, find the exact number. Is that enough information? Or might I want more? Would I know if that's significant? Nah, I need that.
Run the numbers, but change your reference then?
I could do that. So I could set middle or upper as my reference, and then the slope that differentiates the other would tell me that. Or I can ask for it as a linear combination. So that's where our friends LinCom and GLHT come in. You're laughing. I'm not sure why, but. So here's the logic. I'm trying to figure out what the mean would be for each of these other groups according to the model. And once I know that, I know what the mean differences are. So note Each group turns on in only one spot. That's what makes it simplify. Beta 0 is always part of the prediction, and so the beta zeros are going to cancel for any comparisons relative to the reference group. It ends up being the slope for the upper group minus the slope for the middle group is what gets us the difference. So that's what I was doing by saying, well, if this group is higher by 10 than lower, and this group is higher by 8 than lower, then 10 minus 8 is the difference of these two. So this slope minus that slope is how I get to the missing comparison. As a general principle, any answer that has to do with the reference group is already in your output somewhere. Any answer that compares non-reference groups to each other, you got to separately ask for somehow. And there are more or less painful ways to do it. I'm teaching you the more direct but slightly more painful way to start, and then I'll promise I'll teach you a faster way later. But I want you to know what the faster way is doing for you. That's the important thing. So I'm writing out like these equations, essentially. Underscore const means I'd like one beta 0, please. I don't need any of this predictor or that predictor if I want the prediction for the lower group. If it's for the middle group, I turn this one on, or I turn that one on. And then the mean differences are directly given for comparisons with the lower group. This is really the only one I'd have to ask for.
Is that a typo or is that on purpose, the -1?
It is not a typo. This is how I am,
Oh, because
because it's beta 2 minus beta 1.
gotcha.
So the minus beta 1 is right here. And then the positive beta 2 is right there.
Thank you.
Yep. And our folks, yours looks the same in terms of the placements of the ones and the zeros. It's just that it's harder to tell what they tie to. But the first column is the fixed intercept, the second column is what multiplies the first slope, and the third column is what multiplies the second slope. But that is a lot for 3:14 in the afternoon, don't you think? I think it is. Yeah, really, All right, any last questions before we adjourn for the day? Then we will pick this up on Thursday. Please finish your homework if you can by tomorrow night and let us know if you need help, okay?
This is good stuff.
All right, cool. Thanks for being here. Bye, Zoomers.
Lots of good stuff.
Bye, Roomers.